right, hello everybody. I'm Rebecca Helm. I'm at Georgetown University, and I will be speaking to you today about a rather different jelly. It's actually a polyp, so please don't judge me too much. But before I get started, I just want to acknowledge this amazing list of people on the slide. This isn't even a complete list, but these are some of the students and collaborators who have been involved in this project. So really, I'm just the figurehead, but they did most of the hard work. So I want to introduce you to these odd and beautiful organisms. These are Velella, and this picture was taken about 3 miles off the coast of Washington State in the USA. So it looks like a beach, but it's actually thousands and thousands of individual Velellas floating on the ocean surface, concentrating in a windrow. So it's rare to see these out on the ocean. We often see them close to shore. And if you were to see an individual up close, this is what they look like. So these polyps have a chitinous sail and a chitinous float that's surrounded by a ring of blue tissue. And this chitinous sail extends from the animal in an angle that breaks the traditional radial symmetry. So these animals have circular or bilateral symmetry, and they come in 2 forms. They come either in a left-handed form, where the sail will traverse from about, let's say, 11 o'clock to 5 o'clock, if you were looking at a clock face, and a right-handed form, that would be 1 to 7. And this mystery of the sail and the bilateral nature of the sail has bothered biologists for at least 200 years. So why do things come in 2 forms? And this isn't just a question of jellies that float on the ocean's surface. This is a question that very much impacts you and me. So we also break our bilateral symmetry, both in terms of your hand preferences, but also in terms of the organization of your organs. So the breaking of symmetry is an important aspect of organismal biology that extends to many different groups of animals. And understanding why certain species break symmetry then becomes a really important general question in biology. So the null hypothesis for an animal like this would be that we see the left and right-handed varieties in a somewhat random and global distribution, right? So you sort of pick up an animal and it can either be left or right-handed. So please forgive me, I didn't realize I did this at the time, but in this presentation, left is blue and right is red. So it's like American politics. So if we have left and right-handed being evenly distributed, this would be the null hypothesis. But many very smart people who I stand on the shoulders of, who came up with all of these great ideas, thought maybe there was more to it than that. So Mackey in 1962 did some observations. He went and plucked Velella from the shoreline and put them in these quiet coves and watched their sail in relation to a ping pong ball that he set right next to the Velella. And the ping pong ball went in the direction of the prevailing winds. And the direction of the Velella was actually at an angle. So in the case of left-handed Velella, they'll move to the left of the prevailing winds. So if you were to imagine then left and right-handed Velella, you could sort of see in your mind how the 2 sail types might go in different directions. And A.I. Savilov at around the same time formulated a similar hypothesis that the left and right-handed sailed animals would travel to different parts of the ocean in relation to the prevailing winds. So if the wind is going in this direction, left will go left and right will go right. So if we look at the major wind patterns, and this is of course a really simplified cartoon, but that's okay, we can work with it. If we look at the major wind patterns and we imagine where the left-handed animals would go, they would move in this direction in the northern hemisphere. So they would move primarily up to the pole. In contrast, if they're closer to the equator on the other side of these gyres, they would move down towards the equatorial region. But no, we're not just talking about the northern hemisphere. So let's look at just the northern hemisphere and what we might expect to see. So in the northern hemisphere, we might expect to see a distribution of left-handed animals that looks like this on the rings. around the gyre. But what about in the southern hemisphere? Well, we have the same winds, but they're going in the opposite direction. So instead, the left-handed animals will be blown into the center of the gyres in the southern hemisphere, right? So you can see them now. They're being blown up with the prevailing winds, except for now the winds that are going from west to east are closest to Antarctica, so they're going to be blown into the gyre. And the animals that are close to the equator are going to be blown down. So we can imagine a hypothesis that now looks like this. Central blue left-handed animals in the southern gyres, and on the borders in the northern hemisphere. And for right-handed animals, we would expect the opposite. So in the northern hemisphere, right-handed animals, according to Mackey and Savilov, would be blown into the gyres, and in the southern hemisphere, they would be blown out of the gyres. So we would imagine a distribution that looks like this. And if you put them all together for these two different forms of handedness, you would imagine a sort of bullseye pattern where we have right-handed individuals in the central northern gyres, left-handed individuals in the central southern gyres. And as you can imagine, if you're a Velella, you kind of want to be in the middle of the ocean. You don't want to be stranding on the shore. So there may be some benefit to being left-handed in the southern hemisphere and right-handed in the northern hemisphere. So in order to tackle this question, we had to think really big. We wanted to get observations from all over the world. And so we built a project on iNaturalist called the Global Ocean Surface Ecosystem Alliance. It's open to everybody, so I invite you to join. We started it 2 years ago. We have 11,000 observations, or a little over 11,000 observations now. So it's been a wonderful success. We're very happy with all the data we have so far. An important aspect of this project I won't be speaking to you about today is that we've trained our volunteers to report absence data. So we hope that over time, we will be able to incorporate these absence data. We also have volunteers, we send out little rulers, and they'll take pictures of the animals in this kind of orientation so that we can then score whether they're left or right-handed depending on location. In addition, we're expanding our program to target people who are going to sea. So we've given now 7 Newston nets to yachters, people with families, scientific organizations, and they're taking data for us. And one of those data collection efforts I'm going to show to you is from Sea Education Association. So this is an educational institution. They took Newston net data for us, and they oriented all the little Velella facing up, and then we can use this to gather left-right-handed symmetry in gyres in addition to on the coast. So in total, I'm going to be sharing with you over 1,000 observations from iNaturalist today. Now, this took an army of undergrads many, many hundreds of hours, so we're actually transitioning to a slightly different method in the future I'll tell you about, but that's what we have today. I'll also be sharing 55 observations from the Sea Education Association, and these were all mapped in the software package R. So just a reminder again of our sort of alternate hypothesis. If the null is everybody is everywhere, then this is our alternate hypothesis. And if we were to look specifically at coastal regions, just with iNaturalist, this is what we might expect our data to look like. So more right-handed animals stranding in the southern hemisphere and more left-handed animals stranding in the southern hemisphere. And then, drumroll please, my one and only data slide is this. So actually, Savilov and Mackey, looks like so far, maybe on the right track. So we have about 6,000 more data points to analyze, but so far the trend seems to be somewhat suggestive that indeed right-handed animals are found in the peripheral of the gyres in the southern hemisphere, and left-handed are peripheral in the northern hemisphere. Now I'm going to remind you what we would expect to see. So here's our hypothesis again. Looking within gyres, so in the northern hemisphere, we expect right-handed animals in the gyre. And if we look at our Sea Education Association data, in fact, that's exactly what they saw. So right-handed animals appear to be central in the North Pacific subtropical gyre, but then of course, once you get into the California current, it's all left-handed animals. So why might this be happening? Well, there are a couple of possibilities. So the first is that it's some kind of balancing selection. So we have a global population of animals, and in the southern hemisphere, one morphology, right-handed, is stranding at a higher proportion, and in the northern hemisphere, it's the opposite. And so as they're mixing across the hemispheres, you may get this kind of selective pressure acting on one morphotype in the southern hemisphere and a different selective pressure acting in the northern hemisphere. It's also possible that we actually have different populations or species. So it's a left-handed and a right-handed version. Now, I'm a little skeptical of this because we're doing some mathematical models where we're actually simulating the currents and the wind. And I don't have any of those data to show you today because they're still a work in progress with a colleague, Nikolai Maximenko. And if they were all left-handed or all right-handed and you model reproduction over time, eventually everyone will strand and die. So at least in our computational models using realistic wind and current simulations, it seems like this balance of left and right-handed may actually be essential to maintaining the species. But we're not done, and we're missing a lot of data. This is an open community project, so we have open lab meetings every month. We have people coming from dive shops and students in high school and college, so we invite you to come. And if you feel so inspired, we need especially data from the Indian Ocean, hello, and gyre regions. As I mentioned, this data scoring is really time intensive. Now, of course, the hot thing to do right now would be to generate some kind of AI program, but I grew up in Arizona where I didn't have access to the ocean and I wanted to be a marine biologist with no way to practice. So instead of using some computational methods, we decided to build a game. So we're now beta testing a game on a platform called Zooniverse. This platform is primarily used by folks at NASA to generate community science data from large pictures taken from things like the Hubble telescope. So I think we might actually be one of the first marine biology projects on Zooniverse. You'll be able to download this game on your phone, and it'll show you pictures taken from iNaturalist, and you can score left or right-handed symmetry. And so that's a nice way that we can involve people. There'll be a forum, lots of discussion, and also get the data we need to move forward. As I mentioned, this work is very much being done in collaboration with Nikolai Maximenko. Here I stole one of his little plots, just to show you how we're able to model, in this case, the central North Pacific subtropical gyre between Hawaii and California, and really break down on a granular level how wind and current patterns may be influencing the distribution of these animals. We're also busy collecting molecular data to test some of these basic hypotheses about population structure. And finally, if anyone is doing culturing, we've been able to keep the jellies, this is the medusa, they're really small, for about 3 months, and they have gorgeous little gonads. It's something I couldn't say at any other conference but this one. So we've got the male over there and the female over there with a single really big ovum. And so we're working on growing these through the life cycle now so we can figure out, how is this sail directionality determined developmentally? Is it plastic or is it perhaps genetically encoded? So with that, the one little data slide that I have, thank you so much for listening to me yam on about jellyfish, and I'm happy to take any questions.